Buenas tardes. Mi nombre es Javier López, soy profesor de la Universidad de Málaga. Le doy la bienvenida al acto de defensa de tesis doctoral. Me acompañan el profesor Asocán de Aalto University y Jesús García de la Universidad Carlos III. Se va a proceder a la defensa de la tesis titulada Mining Structural and Behavioral Patterns in Smart Malware. El autor de la tesis es Guillermo Suarez-Tangil y los supervisores son, o los codirectores de la tesis son Juan Tapiador y Pedro Pérez. Voy a darle a continuación la palabra al profesor Jesús García, que va a leer la normativa. La defensa se hará en inglés y también el turno de preguntas se hará en inglés, una vez que termine eso. ¿De acuerdo? Jesús.
Muchas gracias, presidente. Pues paso a leer la normativa aplicable a este acto de defensa de tesis doctoral, que viene del Real Decreto 99/2011, de 10 de febrero. Son dos artículos. El artículo 14.4, la tesis doctoral se evaluará en el acto de defensa que tendrá lugar en sesión pública y consistirá en la exposición y defensa por el doctorando del trabajo de investigación elaborado ante los miembros del tribunal. Los doctores presentes en el acto público podrán formular cuestiones en el momento y forma que señale el presidente del tribunal. Y el artículo 14.7, el tribunal emitirá un informe y la calificación global concedida a la tesis de acuerdo con la siguiente escala: no apto, aprobado, notable y sobresaliente. El tribunal podrá otorgar la mención de cum laude si la calificación global es de sobresaliente y se emite en tal sentido el voto secreto positivo por unanimidad. La universidad habilitará los mecanismos precisos para la materialización de la concesión final de dicha mención, garantizando que el escrutinio de los votos para dicha concesión se realice en sesión diferente de la correspondiente a la de la defensa de la tesis doctoral.
Thank you very much. With the consent of the committee, I hereby proceed with the presentation of this PhD thesis. This thesis focuses on the context of security, and more precisely in the context of security in smart devices. And to this end, we explore the problem of malware attacking these devices. In this presentation, I'm going to first motivate the importance of these devices, and then I'm going to introduce the main problems and the main objectives of this thesis. Then I'm going to, excuse me. Then I'm going to present each of the contributions that comprises this thesis, which are divided in two fundamental blocks: the foundations of and tools of this thesis, a static-based analysis called Dendroid, a dynamic-based analysis called AlterDroid, and a cloud-based analysis technique called MeterDroid and TargetDroid. Without further ado, let me put this contribution in context. Smart devices are rapidly emerging as popular appliances with increasingly powerful computing, networking, and sensing capabilities. Smartphones are currently one of the most popular elements. However, we can still find other smart devices, such as the Smart Fork presented at CES conference last year, which allows users to monitor their consumption or alimentary habits and suggest better ways to lose weight. If we compare the popularity of some of these devices depicted in the graph in logarithmic scale, we can observe how many of these devices, such as Android or iOS, has in few years outsell the number of personal computers during all their history. The popularity of one of the key elements behind the popularity of these devices is their mobile nature and their pervasive user connectivity, which allows devices and users to compete, communicate, and obtain a situational awareness of the device of the user. This is done through a number of software layers and an operating system that runs inside this device. One of other key element behind the popularity of these devices is that precisely the incorporatability to install third-party applications through online markets. Some of these markets already count with billions of applications, such as Google Play. Smartphones are currently the platform of choice for users. However, we are finding other new smart devices that they are appearing at a steady pace, such as Google Watches, glasses, or wearable computers. Between all these devices, currently, Android is the most popular operating system, also including malware for wearables, Android for wearables. It's precisely the popularity of these devices, together with their ability to incorporate third-party applications, what poses strong security and privacy issues to final users and infrastructure operators. These issues are materialized in the form of malicious applications or sometimes dubious applications with access to the services of the device and can monitor the information of the user. This has risen to new security problems such as the exfiltration of personal information or traceability issues. The rapid growth in popularity of these devices has come hand by hand with a similar increase in number and sophistication of malware. If we compare the popularity of these devices depicted in orange in the image with the number of malware samples reported attacking different platforms, we can observe an interesting shift back in 2009 and 2010 from Symbian to Android, as this was becoming the platform of choice for users. This property can be easily explained by understanding the malware as a great industry that seeks economical interests. In fact, the bigger is the potential impact of an attack, the higher is the potential revenue that the malware can obtain. It's precisely this correlation what explains that Android is de facto the platform of choice for malware developers and security researchers. In fact, during 2012 and 2013, we have observed an increase on 100,000 malware samples reported, and between 2013 and 2014, an increase on 700%. It's important here to highlight that this increase is only the number of malware samples reported, as not all the malware is being discovered. We believe that these numbers could be orders of magnitude higher. This is the reason why this thesis focuses strongly on smartphone and more precisely uses Android to develop most of the proof of concepts presented in this thesis. However, our proposals and conclusions can be applied to smart devices in general. Based on all this, we've seen that smart devices have increased in growth and in popularity, and the number of both goodware and malicious applications have also increases very much lately. Additionally, we have seen that we are observing an increase in sophistication of in the malware that is currently being discovered. And based on all this, this thesis focuses on the one hand on analyzing a large scale of applications where the developer and the human analyst has to be confronted with the challenge of analyzing many applications. And also when the malware analyzer is facing an opponent that is capable of apply reuse-oriented techniques that allows them to manufacture malware very easily. Additionally, we also find the challenge here not only on classifying malware or identifying goodware, but also understanding some term called gradeware, which is actually those kind of applications that cannot be classified as goodware or malware without understanding the preferences of the users. Additionally, we are observing here that malware is getting very advanced in behavior. We are observing strong obfuscation techniques, and also we are observing malware that is targeting specific users. Based on all this, we have identified the fundamental need of providing a smart analysis and detection technique that will allow the automation of this analysis with a special focus on intelligent instruments that would allow an easy and a fast analysis of malware. To this end, the main objective of this thesis is to develop a set of techniques that assist the security analysts and final users during this analysis. Additionally, smart devices, the analysis of this malware should also be automated and in the identification of a smart malware. Based on all this, objective, we have proposed three partial objectives, which are the study and evolution of current malware analysis and detection techniques, to develop a number of methods to better analyze malware in large markets with a special focus on intelligent instruments and a special focus on the automation of this analysis, to facilitate the analysis of complex smart malware, understanding as complex malware the one that is targeting user-specific actions and the one that is able to hinder its detection and to difficult the analysis using advanced obfuscation techniques. Additionally, it's also desired to detect malware that exploits some limitations of this platform, such as the energy consumption constraints that this devices has currently. Based on this, I'm going to walk you through each of the contributions of this thesis. First of all, I'm presenting the foundations and tools of this thesis. And to start, we first present a comprehensive analysis of the evolution of malware in untrusted devices and current detection techniques. Current traditional classification systems are rather imprecise due to the complexity of the malware and the application of user-oriented techniques, which allows developers to create new malware samples very easily. In this contribution, we have proposed a malware characterization that is not based on those terms that they were applying before, such as virus or Trojans. Basically, we identify three main building blocks to identify the attack and behaviors of a malware, to identify the distribution infection, and to identify the privilege acquisition. Currently, most common attack goals and behaviors are the exfiltration of personal information and the misuse of several services, such as text messages, in order to gain a profitable economic. And this malware is typically distributed through the market. Even big markets such as Google Play are finding a lot of difficulties to analyze all the samples that they are receiving every day. So do this malware developers simply have to upload their samples to online markets. Furthermore, we are observing a very common technique called repackaging, which allows malware developers to download an application from a legitimate market, piggybacks a malicious component into an application, repackage it, and upload this to an alternative market without charge or free, without charge, for example. This way, users are confronted with a lot of applications that they don't know actually if they are malicious or not. Once the malware is distributed in the market, there are also another distribution infection vectors, but this one is the most common. Once the malware is distributed in the device, there are a number of techniques to obtain a privilege acquisition and to bend the platform security mechanisms. Based on all this, many research proposals have suggested new and better ways to analyze malware. Basically, malware detection is a complex process that pulls together monitoring, analysis, and identification tasks. In this, in the thesis document, you can find an in-depth analysis of most important current techniques analyzing and detecting malware in the literature, and how they match with the with the taxonomy that we present in this contribution. Basically, the most common techniques used are, on the one hand, static analysis, which allows to identify and to study the code of an application, and dynamic analysis, which focuses on the behavior of an application. Additionally, we can also find several expert learning and machine learning algorithms that are able to better analyze malware samples, and this can be done typically locally in the phone or distributed and offloaded in the cloud. Based on this study, we have identified the need of providing a fundamental tool set that would allow better research and that would allow researchers to contribute in a better way to the community. To this end, we have developed a research laboratory which comprises together most cutting-edge techniques presented in the literature and implements most of them. We use several methods to analyze malware in the device of the user, to analyze malware in the virtual device, and to replicate and to synchronize both the physical device and the virtual device. The architecture of this laboratory is presented in this slide, and it's been used through all of the contributions of this thesis, and its main objective is to facilitate the analysis of static malware, to automate the repackaging of malicious samples, to guarantee the isolation of virtual environments when we are applying dynamic analysis, to automatically allocate several virtual machines, and to automatically install malicious applications to test this one in the laboratory, to parallelize the execution of different virtual environments, to automate the interaction between our testing environment and the virtual device, and to support the replication of the synchronization of the physical device and the cloud. Based on this contribution, we have published an article in IEEE Communication Service and Tutorials. Next, I'm going to present the second contribution, which is called Dendroid, which applies a new static-based technique to better classify malware samples into families. Human-driven analysis is currently very challenging, as these ones are confronting to the problem of analyzing a lot of applications every day. This is especially challenging also when the analyzer, the human analyst, has to study and dissect new malware samples that he hasn't seen before. And this is also very challenging when the malware, when the human analyst contains a big amount of applications and wants to categorize them and classify them into families. As I mentioned before, malware development is an engineering process that applies a reuse-oriented technique, which allows malware developers to manufacture samples very easily. In this context, data mining can efficiently deal with this problem and can automatically analyze and classify unknown malware samples and obtain the relationship between them. So in this contribution, we have first extracted a high-level representation of the methods of an application. This is done through a technique called control flow graph, which actually represents all possible execution paths that a program might traverse during its execution. And this is done through the grammar that can be seen in this slide. Based on this representation, we have built an atomic component that we have called a code chunk that will be used through this contribution. In fact, we have analyzed several statistical features of a data set comprising 33 different malware families, and that altogether contains more than 80,000 code chunks in this data set. And we have analyzed these several statistical features such as the number of unique code chunks, the number of redundant code chunks, the number of common code chunks, and the number of discriminant code chunks. In the thesis document, you can find more details about this analysis, and it can actually be summarized in this graph. We have observed from this study that almost 80% of those code chunks can only be seen in one family, whereas there is a small, very amount number of code chunks that can be seen in all of those families. This suggests that only using a few number of code chunks, we can easily characterize a malware family based on this information. However, these features, these statistical features, are not very robust when we are dealing with new malware samples that we haven't seen before in our data set. To this end, we adapt to our problem various numerical indicators well researched in the field of information retrieval and text mining. More precisely, we have represented the importance that a group of elements have over a corpus of objects. More precisely, we have used two indicators, which are code chunk frequency and code chunk inverse family frequency. These two indicators, when combined together, gives you an idea of how many times a code chunk appears in a malware family, provided that does not appear in the rest of the malware families. This together gives you an indicator that measures the importance that a code chunk has for a malware family. So based on this, we have built our system. We have built Dendroid, which comprises two main blocks, the analysis block and the classification block. The analysis block aims at analyzing a given malware dataset and understanding its relationships, and the classification dataset aims at classifying an unknown malware sample and to see if it can be categorized as one of the malware samples presented in the original dataset. So to this end, we have extracted all the code chunks mentioned before from this original dataset, and we have also extracted our space vector, which is represented by a vector per family that contains the importance of every code chunk for this family, as I mentioned before. In this, once we have this representation, it's very easy to measure the distance between one vector and another vector by measuring, for instance, the angle between both vectors. In this contribution, we have actually used the cosine distance. Once we have a measure of the distance between two different families, we can actually measure the similarity between them. In this graph, we represent the similarity between the different malware samples, and we can the malware families, and we can here observe, for instance, that there is a big group here of malware samples that they are very similar together, meaning similar depicted in black. These malware families are not called by chance exactly the same. It's because they are very similar to each other. It's called Droid Dream Light, Droid Kung Fu 1, Droid Kung Fu 2, Droid Kung Fu 3, and Droid Kung Fu 4. Additionally, we can also observe here that there is an application called Baseband Bridge, which is very similar to an application called Answer Bot. Once we have also a measure of the similarity, we can apply hierarchical techniques. In this contribution, we have applied single leakage hierarchical clusterings to understand the evolution of malware. More precisely here in this graph, we can observe how base bridge and server board are indeed very similar. And additionally, we can see that DroidKung-Fu1 and DroidKung-Fu2 are related between each other. And in parallel, DroidKung-Fu3 and DroidKung-Fu4 are related to each other. And all four together have a common ancestor, which is actually related with Gold Dream. This information is very useful for the malware analyst, as understanding how a malware family is similar to another malware family can give him new ideas to approach the detection of this other malware family and apply similar countermeasures. Additionally, we have also tested our system. We have also used a system to classify and characterize unknown malware samples, and we have used the nearest neighbor classifier. And to evaluate our classifier, we have used cross-validation, and the results can, as we can see in this table, are very promising. In fact, we can see that most of those malware samples has not been misclassified. They do not include in a classification error. However, we can see here that there is an amount of malware samples that are misclassified, and actually are those malware samples that they are very similar to each other. To conclude this contribution, we have seen that text mining is suitable for classifying malware. More precisely, we've seen that we can, but by measuring the similarity of families, we can classify unknown malware samples into families. We have also seen that hierarchical clustering gives you a good representation of the evolution of different the families, and can also give you a graphical representation, which is indeed very useful for malware analyzers, which is based on the phylogenetic evolution of the malware. Finally, we've seen that this technique is very important, and it's very easy to for automating malware into families, and can be done in a fast, scalable, and very accurate way. As a result of this contribution, we have published an article in Expert Systems with Applications. This third contribution, called AlterDroid, proposes a new dynamic analysis technique to identify obfuscated malware and to identify its behavior. Recent malware tends to hide and obfuscate its functionality in order to hinder static analysis. As we take, for example, the malware sample mentioned before and server bot, we can see that this malware sample contains between the resources of of the application a file called install.png. If you better inspect this file, instead of observing that there is an image, you can observe that it's a payload that is heavily obfuscated. Furthermore, traditional dynamic analysis techniques provides an holistic vision of the behavior of an application, and the malware analyzer, it's very difficult for him to understand if a common behavior, such as connecting to the internet, could belong to a malicious component or could belong to the good part of the application. This is especially challenging when we are dealing with repackaging malware. In this contribution, we have proposed a technique called differential fault analysis, which is very similar and based on a technique called fusing used in software testing. Basically, differential fault analysis is divided in two main modules: fault injection module and differential analysis module. Given an application that we want to analyze, we first extract all those components that could hide malicious functionality, and we inject a fault. We modify semantically those files. For instance, if we are modifying an image, we modify only the pixels of that image in order not to corrupt the file, and then we execute together with the original with the original malicious application, and we compare the difference in the behavior of this application. To illustrate how this technique can facilitate the analysis of complex malware, we have studied 3 representative cases of Android malware using obfuscation techniques: Droid Kung Fu, Ginger Master, and Anserver bot. Droid Kung Fu, for instance, is one of the major Android malwares, which uses a common exploit called Rage Against the Cage. It's a malware family in this its malware sample in this family encrypts this payload using a different key. So if we, for example, analyze the behavior of the application without modifying it, we can observe that this application connects to the internet, leaks some personal information, and access to several files, input-output file. If we apply a fault injection over the component that contains this malicious payload, we can execute again this application. We can see here that the application is only reporting input-output behavior. Thus, we apply in differential analysis, we can conclude that the reminder behaviors that were not seen before were actually because of the malicious component. Based on this technique, we have built our system. We have built AlterDroid, which aims at automating the analysis of this type of malware. This system has 2 modules, as I mentioned before, and first extract all those components of interest, and based on those components of interest that they could actually hide malicious information, we select a number of fault injections, semantic fault injections, as I mentioned, in order not to corrupt the file, and we repackage together these components and build again an application. Then we execute in parallel those 2 applications, providing the same input to both of them. Then, based on the activity signature reported by each of these executions, we compare the difference, and based on a given pattern rule set, we report to the user or to the malware analyzer the results. So we have evaluated our tool against those malware samples that I mentioned before, Droid Kung Fu, Anserver bot, and Ginger Master, a big number of these applications, and we have seen that our system can very accurately identify those components that they were hidden, obfuscated, malicious components. Additionally, we have also tested our system on to see how would it behave when we automate the analysis in large markets. We have actually extracted several malicious applications from a repository called VirusSer, and we have downloaded about 3,000 applications from an alternative market called Aptoid. As a result of this analysis, we have seen that on average per application we can observe about between 145 components of interest and 284 components of interest per application. We can also observe that if we analyze the overall number of components, we can see that all those datasets contain a big number of images, and additionally we can also find that there is a big number of images that they do report to be an image, but they actually don't. They are not actually images. If we apply differential fault analysis and study the results given the number of rules that we have injected in our system, we can observe that from those 3,000 malware samples in VirusSer, almost 2,000 of them were reporting data leakage components. On the other hand, in Aptoide, we were observing that there were about 669 components reporting data leakage. We could also observe that in Aptoide, in VirusSer, we found several components using SMS as part of the malicious payload. We have also measured the performance of our system. Basically, the performance of our system depends on the number of components of interest and the number of fault injections that our system is going to apply for this application to be analyzed. We have also built a search component in order to reduce the complexity of this search, and we have reduced, as can be seen in the image, to logarithmic scale the time that requires to identify one component of one malicious component within the components of interest. As an example, if we analyze a malware that would contain 100 components of interest, which would be more or less here, and would contain about 10 fault injections, which is depicted in blue, and executed during 120 seconds every dynamic analysis, we can observe here that the time that requires to detect this malicious component within this application is of 5 minutes. To conclude this contribution, we can see that AlterDroid can be used to automatically identify malicious components. We have seen also that current static analysis techniques are not very efficiently when dealing with obfuscated malware. We have also seen that current dynamic analysis techniques provides an holistic vision of the behavior of an application, which sometimes is very challenging for the analyst to identify those malicious those behaviors as malicious. And we have seen how differential fault analysis is a good complement of these both techniques and can be used to automatically analyze this type of malware. As a result of this contribution, we have published an article in IEEE Computer, and we have submitted an extended version of this article to IEEE Transactions on Mobile Computing. While the first group of contributions aim at analyzing malware in large-scale scenarios, this very last group of contributions focuses on detecting malware on the device of the phone. To this end, we first explore the suitability of the cloud to do this task, and we then propose TargetDroid. Many security applications can be reduced to the problem of separating malicious from non-malicious activities. This task is very heavy consuming and is very challenging actually when it's performed in devices with a strong energy consumption constraints. To this end, many recent proposals have suggested the idea of using the cloud to externalize all these tasks. In this contribution, we aim at responding this question. Is it better to externalize this information provided that we have to communicate and we have to transmit to the cloud many information in order to be able to analyze it? So in this contribution, we first evaluate the energy consumption trade-offs of several anomaly detectors using machine learning. In fact, a machine learning system comprises 4 different tasks. First, the feature extraction monitors the behavior of a user and processes that information. Based on that processing, extracts a number of vectors that are used to model the normal behavior of an application, and that, based on that model, then is tested during detection time. So given all these tasks, we have analyzed the power consumption that would take to execute every single of them in a real device, and this can be represented in the graph that we can that is depicted on the leftmost side of the image. And also we have measured the power consumption that it takes to communicate and to transmit 1 byte over the network. In fact, if we analyze different parts of this machine learning anomaly detector and different algorithms, we have actually used decision trees, we have used clustering systems and statistical classifiers. Based on this, we have obtained 3 main conclusions. The algorithm used to analyze this type of behaviors matters. There is a huge difference between some algorithms and others. We can also observe that there is also a big difference between training those algorithms and testing those algorithms. And we have also observed that the consumption that it takes to analyze scales with the number of features that we are modeling in our system. Actually, scales linearly. We have also modeled the power consumption that it takes to transmit 1 single byte, and we have seen that the latency of the network is very important in order to evaluate this power consumption. Based on all this experimental evaluation, we have obtained an analytical model using regression, and based on this model, we have studied different strategies depending where this information is placed, locally in the phone or remotely in the cloud. We have also evaluated different parameters of our detector using different frequencies for the training and different frequencies for the detection, and several different numbers of features for this detector. We have actually evaluated 4 different strategies, which is computing everything locally in the phone, offloading the detection, offloading the remote, the training, and computing everything in the cloud. In the thesis document, you can find more details on how this how these strategies have been compared analytically, and the conclusion of this study is that externalizing everything to the cloud is by far cheaper than computing everything in the phone, despite all the synchronization efforts that we should spend. Additionally, it's important here to highlight that computing everything locally it could be very interesting for some users that would have privacy concerns and privacy issues and wouldn't like to externalize everything in the cloud. So to this end, we have evaluated a case study of detecting repackaging malware when computing everything locally in the phone and computing everything distributed in the cloud. If we analyze a task that would last 10 minutes, if we imagine we could detect this malware in 10 minutes, we can observe here that computing everything in the cloud is several orders of magnitude more expensive than, computing everything locally in the phone is several orders of magnitude more expensive than computing everything in the cloud. Even if computing everything in the cloud is cheaper, we can still find that if we compare for a time span of the same minutes, if we compare this consumption with typical applications used in the phone, we can observe that this consumption is several orders of magnitude that using a detector. So to conclude this contribution, we have seen that externalizing everything to the cloud is by far the best option. It's best than computing everything locally in the cloud. Actually, several orders of magnitude, and this is probably due to the fact that communications are very efficient and in current phones, and also due to the fact that the parameters needed to build an anomaly detector, a real anomaly detector, could have high operation frequencies that consumes a lot of battery. Additionally, we have seen that there is a substantial big difference between different machine learning algorithms, and they are much more heavy consuming when compared to normal applications. To this end, we have concluded in this contribution that there is a need to research more on lightweight detection machine learning algorithms, and actually algorithms that could have hardware support, as the communications do have, in order to reduce the consumption of these tasks. As a result of this contribution, we have published an article in Pervasive and Mobile Computing. Finally, this very last contribution uses the conclusion provided in the previous contribution and uses the cloud to detect targeted malware. Malware is currently becoming more and more aware of the context, and malware is actually using very complicated triggering conditions in order to evade, in order to hinder dynamic analysis. Some of these typical wake-up conditions could be that the user is present, meaning that the user switch on and switch off the screen, but there are other more complex features such as the location or the time. Examples of this malware could be, for example, seat zone and toughness, which listens respectively to SMS messages and locations of the user. This way, providing a technique that would be a general framework to detect targeted malware is a very complex task, as we would have to inject all possible, we would have to test all possible combinations of different type of context of the user. So in this contribution, we have approached this problem by centering this task in the user. We have modeled the behavior of a user, and based on that model, we inject those behaviors into a virtual device. So this way, if the user would like to know if a malicious application would be tailored and will be confectioned to target his own device, we could actually identify it without actually exposing the real phone. So in this contribution, we have first made an experimental work analyzing what type of events we can find in Android devices, and the conclusion is that we can find that there is a very small number of events that they are repeated very frequently, and actually the transitions between those events tend towards those ones that they are repeated very frequently. If we analyze the distribution of this graph, we can see that it's a scale-free graph and follows a power law distribution. Based on this study, we have modeled both the usage how a user uses his phone, and the context of this phone. And we have used a stochastical model. More precisely, we have used Markov model chains to represent this information. This way, we can represent actually the importance or the frequency on how those events change from one place to another. This way, in our testing environment, will be those important events will be injected and will be tested faster. Based on this, we have built our system. We have built target.dot, which first extracts the behavior of users, the usage and the context, and based on that replicates the device of this user, and based on that replica, it generates several virtual environments, and based on the model of this of the user, we test stochastically this model in the cloud. So we then collect the evidence of this malware, and based on the preference of the user and a well-known and defined risk assessment function, we can provide feedback to the user. We have evaluated the performance of our system. We have first measured the time that takes to inject several all these events into the cloud. We have actually observed that injecting an SMS message takes about 3 seconds, and we have seen that injecting a geolocation event takes the order of milliseconds. And based on an average of this information, we have generated different models of the user, and we have measured the time that takes for our system to cover most important or cover all of those transitions between different events in the model of the user. We can observe here that when using Markov model chain, this time, the time that requires to test almost all the coverage of the model of the user, is very small when compared to other type of networks such as Erdos-Renyi. In fact, the network that we are testing here in blue is a Barabasi-Albert network, which follows a scale-free distribution, such as the ones found in Android. We have also seen in this evaluation that this technique increases its efficiency when used in conjunction with the cloud. In fact, if a user would have only 10 minutes to test if an application is malicious or not, if we use only one replica in the cloud, it will take in 10 minutes. We will cover the 42% of the behaviors and the combinations of behaviors of these users. However, if we use 10 clouds in parallel, we can reach up to the 83% in 10 minutes. To conclude this contribution, we have seen that stochastical behavior is a very robust building block to thwart targeted malware. We have seen that detecting targeted malware requires very smart inputs, and determining those inputs is a very complex process that can only be feasible when using user-centric approaches. We have also seen that using Markov model chains is very efficiently to reduce the search complexity of these scenarios and to test very fast the models of the user. And we have also presented a system that is able to characterize and model the usage and the context of the behavior. This is all this system, when using at the same time of a well-defined known risk assessment function, can be used to automatically detect targeted malware. We have also seen that this technique is very powerful when used in conjunction with the cloud. To conclude this contribution, we have published an article in Suarez conference. Finally, I'm going to present the conclusions that arise from this thesis. We have seen that there is more malware than ever before, and this is getting increasingly more sophisticated. In this context, we have addressed the main objective of this thesis, which was divided in three partial objects, which was the study of the evolution of malware, the development of a number of methods and techniques to better analyze malware in large-scale markets, and to facilitate the analysis of complex smart malware. We can see that all of the contributions of this thesis approaches one or more of these objectives. As a result of this thesis, we have published or submitted all these contributions to top-ranked journals and conferences in the area of security. Also, every and each of these contributions have been published in one of these venues, except for Metadroid, that we are still waiting for feedback from the community. Also, as a result of this thesis, I have done 2 research visits to well-known researchers on the area of security, and as a result of each visit, we have published 1 or more articles. Additionally, before starting my PhD during the master's degree, I have also worked in several research lines in the field of security, more precisely in cybersecurity, and I have published a number of articles in this context, and this is a research line of my interest as well that will continue through time. Additionally, during this period, I have also taught many courses, many lessons, all related with security, especially related in mobile device security and analysis of malware. Finally, to continue the work that we have presented in this thesis, we propose a number of future works. The first work is very related to the contribution called AlterDroid, and studies malware that could use more complex hiding techniques, such as the one used with steganography. And we have actually crawled several thousands of applications, actually about 30,000 of applications, and found very interesting results that we have submitted to Inscript conference. Additionally, we have also seen that users do not have an efficient way to trust in software. To this end, we are approaching several ways to solve this problem. We are actually currently working on some of them to better provide a trust mechanism for users to know and to understand if they can install an application on their device. Finally, additionally, we also propose to analyze malware in other smart devices with special focus in implantable medical devices, which is a type of device that is very important. We also propose several methods to be applied together with malware analysis, such as forensics analysis and cooperative security, which all combined together could provide better ways to analyze malware. Finally, I would like to thank you all for your attention, and I remain at the disposal of the committee for any further questions and discussions about this.
Thank you, Guillermo, for the presentation. So we start now the phase of questions, and we'll start with Professor Jesus Garcia.
Thank you very much, President. In the first place, I would like to congratulate the candidate for the quality and the extension of the work presented here. I have liked a lot the document. I found very instructive and presented clearly the problem and very exhaustive analysis of all the threats and characteristics of cyber security threats in this domain of smartphones. So I appreciate a lot this document, and I also appreciate the work done to develop the analysis tools, the laboratory to experiment with real systems, real application, and validate the results obtained in this research work.
Thank you very much.
Very welcome. I have several questions. I would like first to start with the connection, the relation between the different strategies and contributions you have presented here. In the first place, with respect to static and dynamic analysis, you have pointed out the problem of obfuscation in the static analysis, then presented the other strategy with the differential analysis. I'm not very sure if there is a connection between these two steps, or if they are applied in parallel.
Yeah, indeed. Actually, applying them in parallel or combined together are much more efficient than only analyzing the behavior of an application, as when you use obfuscation technique, it's almost impossible to obfuscate all your traces and all your components. So this way, static analysis techniques are also important to combine together with dynamic analysis.
Okay. And analogously, with respect to the last the contribution, behavior triggering, I have understood the process to generate the different combination of context variables, but I have not very clear which is the process to detect the threat. If you apply any of the previous techniques, or it is a different technique.
Okay, that's a very good question. We haven't gone through it very importantly in this contribution, as we were focusing more on the part of the evidence generation and those parts. And we are working on an extended version that is focusing on this box here, this component called risk assessment function, which is key for this problem. And it's a contribution itself because it requires also information. In this contribution we have provided, based also in the ones presented before, we have provided a number of rules that would detect several obfuscated malware and several of these behaviors. But this component here is more extensive than the one presented in previous contributions, because it uses and it needs the input of the user, and modeling this input and modeling this preference for the user is important to actually detect. For instance, if we for some users, for example, Facebook could not be actually classified as greyware or as malware, but some other users, depending on their context, they might not want an application that would access to their pictures and upload this to the network while they are working, for example. So for some environments, such as bring your own device at work, Facebook could be actually be behaving as a malicious component in this context.
And would it be possible to apply here some machine learning strategy to detect the anomalous output of the system in certain conditions?
Exactly. Actually, that was the way that we were thinking on approaching this problem. We are working on obtaining a huge amount of information from users, and based on that, based on machine learning, because if we have a lot of input, we could actually better define this strategy. So definitely machine learning would be a good tool.
Okay.
Thank you very much for your comment.
Okay, thank you. With respect to the static analysis, I have seen the detector is mainly based on a nearest neighbor technique to analyze the code chunks. First question I have here is, these techniques are quite sensitive to the relevance of the attribute. I don't know if you have performed analysis of the attribute relevance or filtering of the attributes extracted for the code chunks before going to the nearest neighbor.
No, we haven't done that part, and we were actually thinking on approaching another contribution based on this, extracting those features, more semantic information, not only structural information. But currently we haven't approached that way.
In this contribution, you present in the document, in page 123, a big confusion matrix explaining all the rate of success. But here my doubt is with respect to the false positives. I don't know if you have used a data set with a normal application and malware to analyze what is the rate of a false positive when you apply this technique.
We have used the only data set that we could retrieve that had malware that was classified already in families. That was the malware comprising 1,200 malware families, malware samples in 33 families. So everything here is malware, and the false positive rate that we can here differentiate is actually when we misclassify between one malware family and between another. We haven't used goodware to see if we could actually if we could misclassify some goodware applications into malicious, and we will definitely research more on that because it's interesting.
And finally, in this analysis, I have a curiosity. It's about the obfuscation. You mentioned that obfuscation is a big problem for the static analysis. I don't know if you can detect the presence of obfuscation when you apply this technique or not.
Yeah. You can. Well, in this contribution, actually, we have one of the components of interest actually measures more or less what you are referring. We have measured the entropy of several files that they were encrypted and they were obfuscated, and we've built a threshold to understand and to realize if an application is actually encrypted or not. So based on that, we have implemented a component of interest that just only activates itself when finding information that could actually be encrypted.
Okay. So you can detect. Okay. And I conclude with a last question. It's with respect to the the conclusion is better to use a replication in the cloud to do both the training and the detection of the malware. Here my question or my curiosity is about the cost of keeping update the replica in the cloud, to the synchronization cost. If you have considered this as a parameter, with how much frequency you have to upload the copy of your device in order to detect as soon as possible the malware.
Actually, we have done indeed that, and we have represented, as we were focusing on anomaly detectors, we have measured that information in terms of the length of those vectors. So when that information is very low, then the consumption is, we have actually input that in our parameters. And an interesting conclusion is here that the energy consumption scales linearly, that as big as, the bigger are those features and that information, the higher is the consumption, and it follows a linear scale.
Okay, thank you very much.
Thank you very much for your comments.
Thank you.
Thank you, Jesus. Now it's the time for Professor Asokan.
Okay, thank you for giving me the chance to ask questions, and let me also congratulate you. It was, in terms of the amount of work, this is clearly more than what I have seen for a PhD dissertation. You have done a lot of implementation, a lot of analysis work on many different topics, and I'm sure your survey papers, for example, will be very useful for the community.
Thank you very much for your kind comment.
So let me start by asking you kind of a more broad or philosophical question. So you mentioned a couple of times that the extent of Android malware is growing. You had this very exponential growth chart, and this is also what you hear from antivirus companies and so on. But what do you think about the actual infection? Like, how big a problem is this in reality? There are, it's one thing to say there are more and more malware being found as malware samples, but are these malware actually infecting user devices, and how is it compared to, say, infection on PCs? So what's your take on that?
I think it's on the one hand, it depends on the users and the targets. I believe that more young people and several contexts would be more at risk in this problem, because they do not actually want to pay for applications, and they go to alternative markets where you can find the same very applications, Angry Bird, for instance, for free, and you install it in your phone. And I think that in those contexts, the problem of malware could be really alarming. However, I think that in other contexts, more concerned users that only install applications that they are well known, and they keep updating their devices, I think that the risk could be minimized on those scenarios. However, if we are talking about Android, for example, that also the platform is very important, we have to bear in mind also that Android platforms, at least the baseband and the more low-level part of these phones are not updated by Google, but instead is updated by the operators. And there are some operators that they do actually not fulfill a responsible way to approach this, and they keep for many years, several versions that they are known to be vulnerable. So it depends on a number of cases. All in all, I would say it's concerning, and it will be more concerning.
But what do you think about the malware problem on mobile devices as compared to malware problem on PCs? Would you say that they are equally serious, or is the extent of malware on PCs is less or more compared to mobile devices?
I think that mobile devices it's more serious for one single fact. There are many more devices as a number in terms of sold devices than personal computers, and in terms of economics, malware is an industry and tries to target those markets where they are going to get a higher profit. So I believe that smartphones are very sensitive in this case. Additionally, users do not have any concern to keep everything in the phone, and also not only they have access to the email or to the personal documents of the work through Dropbox, etc., but also the malware has situational awareness of the user, which is more interesting for malware developers than personal computers that do not come with sensors to hear or to measure the temperature, etc., etc. So based on those facts, I would believe that in mobile devices the malware has boomed, and it's due to those facts.
So I would agree that malware on a mobile device has the potential to cause much more harm than on a PC. Nevertheless, the extent of mobile malware infections are known to be less compared to PCs, right? So there have been papers, for example, from Georgia Tech, NDSS 2013, which said infection rate is something like 9 out of 1 million devices, which is much less than in PCs. So you touched this in the beginning of your thesis. What could be responsible for this relative safety of mobile devices today? I mean, this might, of course, change.
Yeah. Well, perhaps it's the fact that knowing the amount of malware that it's actually there, it's not easy, and perhaps I haven't gone through that study. I'll be thrilled to read it more in depth, but perhaps we are not aware of what is actually going on. But also because smart devices are relatively new technology compared with personal computers, and this industry sometimes, the malware industry sometimes tends to reuse their efforts, and if they do, if you can still find many personal computers there, and you have a lot of infection components, and you can build more malware attacking those personal computers, maybe the industry hasn't moved yet. But in any case, I think malware in personal computers is still a very interesting research area, and actually we are moving towards there as well, because there is still many challenges to face.
Very good. Yeah. So I guess as long as the malware attackers or malware developers will go where the money is, and the shift might be slower in that sense that it hasn't happened yet, but it will happen that at some point there will be malware on mobile device will be a much more serious problem.
And also, if you allow me to continue with this discussion, also I think that the sooner enterprises are allowing more policies of bringing your own device, or I think malware developers also might shift towards there, because sometimes money in terms of malware development is not always in a big amount of users, also in the resources and the money that could. So many enterprises have a lot of value in their personal computers, in their servers, and that's why malware there is still of great interest.
Okay, so you didn't touch this in your presentation, but in your thesis you had a very extensive classification of different attacks in the beginning. I think it was somewhere like section 2.4.2, I think you had like this table. So how did you select those? So you looked at some number of malware examples, and then you classified them as multipurpose malware or whatever. So how representative are those samples of malware that you looked at, and what was the reason for picking that particular set?
Let me see if I know exactly which table are you taking. Is the one that relates the features of the detection with malware samples, or?
This is the one that is in table 2.2.
2.2. I could
page 46, I think. So you had a list of page 47. So this table here. So you picked a.
Oh yeah, yeah, yeah. That in that table, for the ones that they haven't seen, we aim at relating and seeing the relationship between the malware that we have found and the malware that we've seen in the literature. With the behavior of the incentives and the goals of that malware, and that classification is based completely on our experience and based also on the documentation that we have learned. And we reckon that classification could not be exhaustive, and it's not intended to be exhaustive. The main idea behind that representation is to show the reader that this relationship sometimes is very complex.
So it's based on your expert knowledge that this is representative. Yes, that's very good. Okay, so then moving on to chapter 4. So I think you showed this. You use machine learning techniques to find out how to group malware into malware families, and then you had ground truth in the sense of you knew malware that was already classified, and you use that to prove that your technique is effective. But then you also went one step further and tried to find this kind of generational relationships, a hierarchical relationship. Did you have some ground truth for that? Did you compare that with what antivirus vendors have said about sort of inheritance relationship between malware samples?
Initially, we didn't compare it. We just we were trying our approach and to see what was happening. But when we got the results, we were reading several articles. There is one from North Carolina that's called Dissecting Android Malware that has an in-depth information about the most important malware samples of this data set. Actually, we retrieved our data set from them, and we could actually successfully see that our conclusions were matching exactly with the efforts that they spent when analyzing physically every single samples. And they were saying that they were using common exploits, and one was based on another because it was using common strategies or ideas to encrypt their payloads, and so we got a very positive results.
You could see that your results match what they had. So this is the mobile genome.
Malware genome project.
Yes. Okay, so then I think in chapter 5, so you had this so you were using this fuzzing technique, this slide 31, I think. So I found this very interesting. I think it's a novel technique, and you seem to have good results. But I was having trouble understanding that. So if you go to the previous slide, so you had...
it goes as slow as the computer is not very fast.
Okay, so you had unchanged version, and then you had a fault-injected version. So my initial understanding was that you take a piece of known malware which has some payload that contains malicious information. Then unchanged version is this unchanged malware, whereas this red lock there is the obfuscated version of that same malware. Is that correct?
No, it's, I mean, both applications are the malware. This one here is the one that is not in red. It's the one that has the obfuscated malware.
Yes.
And this one is the same malware with a modification over that component. So both of them are obfuscated, but the second one has an injection of a fault into that component.
That you did using your tool. Okay. So then if you go to the next slide, I see that the lines connecting these black circles, that's what you would see if you run this original application.
Exactly.
And the rest is what you see if you run the fuzzed application, fault-injected. So then explain to me, what is the green box? What is the goodware activity?
Okay. In our system, we're actually analyzing repackaged malware.
I see.
So repackaged malware, as mentioned before, and as you know, it's generally has most of the core of the application is a goodware application, and there is a piggyback malware that has been injected into that application. So in green here, we depict the behavior of the of the repackage, the original application that was Goodware. So that's the main difference.
So there are, in fact, 3 applications here: the good applications, the repackaged one, and the fuzzed repackaged one.
Exactly.
I see. Okay. Very good. So, like I said, I really like this technique. And,
thank you very much.
Okay, then if we go to chapter 6, so you had I think it was slide 31, where you had this. Is it slide 31? You had a chart showing with and without TLS, with and without
the power consumption.
Power consumption, right? So
yeah, it's this
right,
one.
this one. So you have with and without HTTPS, but you don't have this open. So link layer security and not having link layer security.
Yeah.
So for some reason you didn't try high latency and no link layer security, or high latency open. Why is that?
We did try, but the results were very similar. And just for the sake of understanding and for depicting this information here, we didn't actually put it, but we made those experiments, and the results were very similar in high latency networks.
Okay, and in the so you have essentially no difference between HTTPS and HTTP, and you explained this in your thesis by saying that the tool that you used, which is AppScope, might be misattributing the crypto costs as sort of system software costs. Right?
That could be one of the options, but also we believe that actually we've measured, we were curious about it, and we were measuring more precisely what was consuming several encryption algorithms. And we found that they are very efficient, that they don't consume very much in these cases. So, although it could be true that the tool would not be properly measuring that information, we also believe that that this information could be correct, and it's actually we have compared our results with other approaches that we were measuring power consumption, both in wireless sensor network, which was very interesting. It was important, and we've seen also that the consumption in this with these algorithms. It's important for devices that they are not that they are very constrained, like wireless sensor network. But in this type of devices, they are very optimized. That all the hardware and the processor already counts with some instructions for help AS to encrypt, and we believe that could be actually very efficient.
So HTTPS is not just computation, right? And in the handshake, it also increases the message size or communication cost.
Exactly.
So it might, your conjecture that the AppScope might be misattributing might in fact be valid. Yeah. And you actually also see that between WPA and not using WPA, there doesn't seem to be much of a difference.
There is either, yeah.
So is it possible that the same kind of misattribution could have also happened for communication costs, that the communications costs that you are measuring may not be accurate because the AppScope might have attributed them to system costs?
I don't believe that there is a problem of attribution, because we were inspecting all the processes on the phone and comparing the consumption that was actually reported by every single of them. We don't. I don't believe that the consumption was put in other processes and was.
Did you use an external power monitor as well?
No, we haven't have the chance to do that, but it could be really interesting to
that
do
would be the way to settle this question, whether it is doing this or not. Indeed. Okay, so maybe my last question is, so I think we discussed this in the previous version. So what you are really focusing on is energy and not power, right?
Yeah.
But can you speculate about where would low power be important? So in your example, it's low energy is what's important. You try to save battery. But what are situations where low power and techniques that have low power would be more interesting?
Just to To explain better, I mean, we focus on energy in this contribution, and we sometimes talk about power because it's the same measure without taking into account the time. And I believe that that I'm not sure if I understood well the question. But basically, when we refer to energy and power, we are talking about the same. More or less the same thing. Just
so power is the rate of change, right? So
yeah.
you can have a low power solution that's actually consuming a lot of energy because
yeah.
it takes a long time.
Oh yeah.
So low power is important when you are worrying about things like heating, for example.
Okay,
so you don't want to overheat, then you have to have a low power.
Okay,
but I guess you are worried about.
That's interesting. I now I get it. And actually, when you're detecting malware in this context, it would be interesting to have high power techniques because you want to be very fast. You don't want to use it during hours. You want to compute fast and
so you want low energy because you don't want to run your battery out, but you might want
high power too.
Okay, so that concludes my questions. And
thank you very much.
Again, congratulations for a good dissertation.
So now it's my turn. Guillermo, let's first me congratulate you for the excellent PhD work. Of course, your supervisors too. I had the opportunity to be in the present during the pre-defense some months ago. Already at that time, the thesis was quite completed, and I could see that during these months there was space for some improvement based on the feedback that we provided to you at that time. I can see that issues raised at that time were considering the new version of the thesis. But still I have some other issues that I would like to ask you. Probably most of them were already included in that pre-defense, but still have some comments and questions. Regarding the taxonomy that you show in slide 17, so I have a question. Is that taxonomy done completely by yourself? Have you been based in previous taxonomies, or actually were there any taxonomies before this one? So what is the genesis of this taxonomy?
Yeah, we've seen taxonomies provided in the literature. However, they were not with the same extent as we were using, and especially because they were general purpose detection techniques used also for personal computers and not smart devices. There were some contributions that they were mentioning in one way or another, almost all these ones, but the ones that we've seen before, they were not the same at this extent. For example, a very interesting way to analyze malware is dependent on the granularity that we haven't seen in other contributions. Also, we haven't seen talking much about the inline reference monitoring, which is a way to detect and analyze malware by repackaging the application, but being repackaged by security experts, where they inject into the application detection systems, and they are actually executed in the same level as the application. And we haven't seen, for example, in other taxonomies, several of these novel strategies.
Okay. So I assume that this taxonomy was included in this first publication of IEEE communication surveys and tutorials.
Exactly.
Okay. Okay. Good. Next question is about Alterdroid. Actually. What I can interpret is that the main motivation for working on Alterdroid is that, as you mentioned, the malware hides and obfuscates its functionality. So I'm not sure if I am understanding. I have a different understanding of obfuscation. This is an old term used in security. I cannot conceive a behavior of the attacker that is not aiming since the very beginning to hide and obfuscate what he's doing. So you evolve from a static analysis to dynamic analysis, saying, okay, we have studied static analysis, but what we are observing is that the malware is hide and obfuscated, and that is why we have to study it from the perspective or more dynamic analysis. But I would say that this is intrinsic, no, in the behavior of the attacker, that he always tries to hide and obfuscate. But maybe if you provide an example of what do you mean by obfuscation of the functionality, maybe I could understand better this.
Okay. What we mean here, obfuscation, is in the more traditional way when they obfuscate statically the code. For example, this example depicted here, this is a payload, this is a program that it's been encrypted and will be only unencrypted during runtime, but we don't mean to we don't refer to obfuscation of the behavior of the application. We refer to obfuscation, static obfuscation. But we have identified that that sometimes when we apply dynamic analysis, the behavior of the application sometimes is really entangled with the original part of the application, with the goodware of that repackaged application. And sometimes it's very difficult to understand if an application is connecting to the internet, if that behavior is part of the goodware or the malware. So what we refer here that there are some limitations on dynamic analysis is that we are not able to make an attribution of behavior to components of the application. To understand, for example, in this payload, to see if it would have some code that would actually connect to the internet and then extract some contacts or some images. So that's, I'm not sure if I responded to the question.
Okay. No, it's more clear the difference, yes. Oh. Thank you. Okay. Another question is related to the automation of malware classification. You state that this is a little bit before in the, slide 27. Yeah, the last paragraph. You say that the results suggest that this technique is fast, scalable, and very accurate. But can you provide some figures about what do you mean for fast, so that we have a better idea?
Okay. I don't have. We haven't measured the time that takes because we have this contribution is purely based in static analysis, which is it's very small. The time that it takes to analyze this information. So we haven't actually provide a formal representation of the time, because our experiments did not incur in very high overhead.
Okay.
So we don't have a formal representation of this.
Okay. Let me ask you, I'm curious about the following. In the thesis and the presentation, you mentioned about the research lab for this smart malware analysis and detection, and let me check, in slide 18, no, sorry, it's 19. 19, right? 19, yes, 19, yes. Yeah, there you say that you have registered the software. So is there any ongoing exploitation of this software registration? And another question regarding the research lab. What does the research lab consist of? Is just only the software? Suppose that I am interested in your work, that I really am. Suppose that I want to do something like you, and I want to learn better what the research labs consist of. Is only software? Is this hardware? Okay. What kind of hardware? How did you manage to put all this together?
Okay. Yeah, we have actually registered the components of this laboratory, and we have get some requests to exploit this malware. However, we haven't currently meet the end of this part, because we are actually going to release as an open source, or at least as a fair use tool, so the research community will actually be able to use it. But let's say, for example, that an enterprise would like to use it and gain profitable economic. Yes, we will. We could actually exploit this this software. And answering to the other question, basically this laboratory is on the one hand it's hardware, but very limited hardware. Used for some of the contributions, such as a smartphone, which is very cheap and inexpensive, and the rest of it is pure software. And basically, this laboratory, in order to have something similar to it, will have to comprise three main tools together. Static analysis techniques that would allow to extract the components that an application has, to unpackage, dynamic analysis component and cloud-based analysis components, at the same time as several crawlers that are able to download applications from Google Play and Google Market and so on. Furthermore, there is also in the thesis document, in case you are interested, a big amount of references referring to tools that they are already available that also do parts of this information, that they are open source, and our laboratory will be soon available for you if you want to use it. So.
Okay, thank you. Let me finish with a more philosophical question. We can see in slide, let me check, I think it's number 10, yes, at the very beginning, and this is the foundation or the motivation of the whole PhD work, how the malware has grown in the last couple of years. Now, and then obviously what you have done in your thesis, you have plenty of very nice software tools to defend against this malware. In the non-computer world, when we have crime, of course we have defenses against crime, but one of the defenses is to try to decrease the level of crime. Can that picture be extrapolated to what we have here, or there is no other way than just to see how this increase and increase and increase forever?
Let me get clear. I'm not sure if I understood the question. You're referring, when you refer to crime,
suppose that when, let's forget about computers. Let's talk about crime in society. Okay. We have here computer crime. When we have crime in society, we can just think about how to defend against crime, but we can also try to fight crime in its origin, try to decrease the crime there. But I don't know if that picture can be extrapolated to this kind of computer crime that we have here, because you can see in the picture ongoing tendencies increasing. So can we expect that in the future it will increase again and again, or is there a way to stop this?
Okay, now I understand the,
or to decrease
the question. And I believe that my answer is going to be, I'm not sure if...
that's why I said that my question was philosophical, not technical.
Actually, in crime currently in society, we can decrease crime using some socioeconomic factors like improving the well-being of a society,
for example,
and those kind of things. But although that could work in the society, I believe in here in IT, it's very difficult, because sometimes the ones that they are pushing towards that criminal activities are sometimes the same responsible ones that rule big companies. For instance, if a new company wants to release a product, would find very useful to send a lot of spam to their users, and to that end, without doing it directly, they could buy some information extracted from malware to obtain real email. So, to avoid and to try to stop increasing this part, we should apply these measures in many parts of the society, but especially focuses on the ones that they use this type of services and pay for this malware to be used.
Okay. So I think there is no other solution than to see how the increasing tendency in the next years, no?
Oh, but let's have some hope in research just to.
Okay. Okay. So I don't have any further questions. Just to conclude that, again, to congratulate you and your supervisors because of this very nice research work with very high quality publications. I think this is really very good. Also for the presentations, from the presentation today and the way how you answered all the questions from the committee. Just for concluding, I have to ask if there is any doctor in the audience who wants to make any question. ¿Hay algún doctor en la sala que quiera plantear alguna pregunta a Guillermo? No. Bueno, pues entonces damos por concluido esta fase y el tribunal se queda aquí ahora para deliberar.
Thank you very much.
Gracias.